So today we're going to talk about two things. One is nuclear winter, the myths, the inaccuracies, and the assumptions behind it. The other thing we're going to do is talk about the radiation content and fallout and a few facts that people really don't know about fallout. Now, the first thing we're going to do is talk about nuclear winter. And when the thoughts of nuclear winter first started, a lot of this was centered around Carl Sagan and some of the other very liberal scientists. They kept on, with the results and selling books and making money and propagandizing. And they kept on refusing to provide the data and the assumptions they used to come up with these theories. Now, I don't think there was anything wrong with the data, but the problem was the assumptions they made in the study. So, to arrive at nuclear winter, you had to have a lot of particulate that stayed airborne for a long period of time, not a short period of time. And when you looked at the distribution of particle sizes, they made a lot of assumptions on the particle sizes that would be produced when cities burned after a nuclear attack. And these particles were the key to the long-term suppression of temperature. And that's where the problem with the theory came. So when you rectified those assumptions, the most that would have occurred would be a temporary suppression of temperature. Now, there's been thousands of atmospheric nuclear tests. So when we look at the results of those, some of those, they had temporary reductions in atmospheric temperature. Some of them they didn't. So it was not a consistent phenomenon. But then again, with large-scale weapons, there's never been a large-scale nuclear weapon that was detonated in a city environment where the city was actually burned. Now, to move forward, the radiation production from a contact burst with a city or a low-altitude burst where the fireball touches the ground, that hasn't really been explored in the public. So we have the rule of 7, where radiation falls based upon 7-fold increases of time the radiation levels have. And this is based on distributions of fallout from actual nuclear tests. Now, this is the rub that's never really talked about. When they started doing nuclear tests, they used to suspend nuclear weapons on steel towers. And the reason they stopped using steel towers is when you have a detonation and the steel is vaporized from these towers in a environment where you have neutron activation, where neutrons are bombarding the steel, you end up with two specific radioisotopes of iron that are radioactive. And the suction of the iron from the tower up into the fallout cloud of the detonation was actually something they could track. And what they found was the content of these iron towers was increasing the radioactive fallout from the blasts that they were doing in tests. So if you take that to the extension, if you go into large cities and you're sucking up concrete, aluminum, and steel, which contains iron, a lot of the radioisotopes you would get from an actual neutron activation in the actual burst area, you would turn aluminum, steel, and some of the constituents of concrete into radioisotopes. And the distribution pattern of those radioisotopes would be different than a burst that was in contact with a forested area, a desert area. And one way that they differentiated the different effects of nuclear weapons on different atmosphere and different environmental conditions is they actually had a 1 kiloton nuclear device that they used as a control. So before a long series of nuclear detonations, what they would do is fire the 1 kiloton device, and they would record the data on how it reacted to the atmospheric conditions and also the environmental conditions. And they used this to extrapolate and compare data. But so what they would do is use the 1 kiloton device as a control to compare the effects between test sites. So in the Nevada desert, the test site there was desert. In the Bikini Atoll, it was tropical, with a lot of foliage and a lot of humidity in the air versus the dry air of the desert. And the way a nuclear detonation propagated is different in those two environments. And what they found is in the desert environment, you would actually create a Mach wave in the blast. So the reflected wave that came down from the nuclear detonation would hit the ground, and it would actually overtake and catch up with the outer wave that was coming off of the nuclear detonation, and the waves were in phase, so they would add together and you'd get much higher overpressure than what was calculated. That effect was found in the desert environment on most of the shots. Now, when you went to the Bikini Atoll, the foliage, the atmospheric conditions, the moisture content, you didn't always get the Mach wave formation. So you can see from that, a lot of the environmental conditions have an effect on blast overpressure and the way that the detonations propagate. So the last thing we want to look at is the terrain conditions and how they affect nuclear effects of a detonation. And what you find is a flat open area, you can get Mach wave propagation, higher overpressure. If you are in areas that are mountainous, that have a lot of valleys and folds or hills, you can have shadowing effects where you can have a nuclear detonation on one side of a hill or a mountain, and you have a safe zone that doesn't get any of the effects on the other side of that obstacle. So these kind of things are used in civil defense planning. And if you look at the two nuclear detonations that occurred on Japan in World War II, one of the two cities was in a kind of a valley-like structure from a geological standpoint. And this had a limiting effect on some of the blast. Now, the last thing I'd like to talk about is with fallout generation. Fallout comes from when the nuclear detonation actually touches or reaches the ground and is capable of pulling debris up into the cloud where it radiates it. So if we look at this phenomena, basically you can have a surface burst which is in contact with the ground. That draws up the second most amount of material into the cloud, and you get the second most severe fallout. Then you have an air detonation where you have an air burst and it's not high enough in the air so that the fireball will actually come down and touch the ground and suck debris up. The next one is an air burst where the burst is high enough in the air where it doesn't draw any particulate up into the detonation. And in this one, you don't get fallout. You do get initial nuclear pulse below the detonation area, but you're not going to get fallout because it's not close enough to the earth to draw debris up. The last one, and the one that produces the most fallout, is a shallow water burst. So if you're in a coastal area around a dock facility, shipping area, naval base, a shallow water burst sucks the salt water up into the detonation, into the cloud, and what it does is it radiates the sodium, and you produce radioactive sodium and also radioactive chlorine. So the salt breaks down into 2 radioactive isotopes when it's bombarded by the neutron flux. This is the dirtiest one, and it's the hardest to decontaminate when you're using conventional nuclear munitions. And this discussion excludes cobalt, because cobalt case weapons are a special case. And we'll talk about them in a different video, because the cobalt case allows you to have a persistent radioactive denial zone because of the half-life of the cobalt. So please comment, and we'll see you on the next video.